Hey there, this is a short screencast on the proof of the quotient rule. So, the quotient rule is a rule we use for differentiating functions that can be defined as quotients of two other functions. So for the purposes of the screencast, we're going to let f of x and g of x be differentiable at some number c, some input c. And we're also going to assume that g of c is not equal to 0. Okay? That's because when we define the quotient function as the function whose values are the quotients of the output values of the two functions, when we plug in x equals c, we don't want to get division by 0, right? So division by 0 would be bad. So that's why we have that additional assumption there that g of c is not equal to 0. So the quotient rule says this. If f of x and g of x are differentiable at x equals c, with g of c not equal to 0, then the quotient function is also differentiable at x equals c. Moreover, the derivative of the quotient function at c is given by the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. So you can see here's another place where we don't want g of c to be equal to 0. All right, so this is what I'm going to do today, or in this screencast. I'm going to prove that if f and g are differentiable at a point and g doesn't vanish there, then the quotient function is also differentiable at the point, and the formula for the quotient looks like this. Okay, here's the proof. I always like to begin a proof with a restatement of the things that we know. So we know g of c is not equal to 0. That's easy to write. We also know f prime of c exists and is given by this limit. And g prime of c exists, and it's given by this limit. And these limits here are just from the definition of the derivative. This is how we define g prime of c. So those are the things that we know. We want to show the function f over g of x is differentiable at x equals c. So that means we want to be able to take the defining limit and show that limit exists. So therefore, we're going to write f over g prime of c. If it exists, it has to equal this limit. So that's the definition of the derivative of f over g, the quotient of f and g. So most of this proof is going to be spent rewriting this in a way that gets us to a place where we can use these two facts that we know. So bear with me, I'm just going to start rewriting. So the first thing I'm going to do is I'm going to take that x over c in the denominator and write it as multiplying what we have by 1 over x minus c. And then I could have combined these into one step. I'll use the definition of the quotient function just to rewrite what was in the parentheses in that way. And now I'm going to rewrite this difference as a single expression over a common denominator. And so you'll see we get this. So that's pretty cool. Now let me just reorganize this for a second. I'm going to switch denominators here. Okay. So what I'll point out to you is that look at this down here. We like the way that's looking because I'm going to swipe back. Because look, we're supposed to end up with the value of g at c squared. And notice what we have. We've got 2 copies of g down there. And you'll see that that will resolve into what we want it to resolve in. So I'm going to let that alone for a while, and we're going to focus our attention here. What I'm going to do in the next step is I'm going to take this and put it upstairs in the numerator. And if you look at it, that's just 0. So I'm going to be adding 0 to my numerator, but a particular type of 0 that's going to be of big help to me. So that's the next step. So continuing those equal signs, we have the limit as x goes to c. So we had this. And then in my numerator, I've got f of x, g of c. And here's where I'm going to put that. And then I'm left over with f of c, g of x. That's all in the numerator, and downstairs is still this x minus c. There's a closing parentheses over there. So what does that get me? Well, watch this. This is where I'm edging toward using the definition of the derivative. All right, so there I just rewrote that expression from the previous step. And if you look at each of these expressions, the first one, look at the numerator. Both the terms in the numerator have a g of c in common, so I'm going to factor that out. And over in the other term, both these have a common factor of f of c, so I'm going to factor that out in the next step. So this is what we get. The limit as x goes to c of 1 over g of x, g of c, times g of c times f of x minus f of c over x minus c. And then over here, I'll factor out this f of c. Okay. And now you can see this is the difference quotient we want to work with, and this is the difference quotient we want to work with. All right. So in the next step, I'm going to use some of our limit laws. So the limit of this whole expression, I can write that as the limit as x goes to c of 1 over g of x, g of c, times the limit of the things in the parentheses. And in the parentheses, I've got a sum, so I can write this as the sum of these limits. So that's good. And now I can use the limit laws again, noting that this is a constant, so I can pull out in front of that limit that's right in front of it. Likewise that's a constant. I can pull it out here. Okay, so let me do that next. So I get g of c times the limit as x goes to c of f of x minus f of c over x minus c plus f of c times the limit as x goes to c. Okay. So here, this is exactly the definition of f prime of c. Okay? That's great. Here, we want g prime of c, almost. Okay, we're almost there. But notice here, there's a plus. In the quotient rule, there's supposed to be a minus. So I'll draw your attention to the numerator in the second summation right here. Those terms are in the wrong order. If you look over at the other summand, in the numerator, it's f of x minus f of c. Here in this summand, it's g of c minus g of x. So if we change that order, then things get fixed a little bit. So what happens when you change the order, you get a minus g of x plus g of c. And we're off by a sign, but if I factor out a minus 1, that becomes a plus, that becomes a minus, and then what I'm left with here is a difference quotient for g prime of c. So that's what we want to do. And then that minus 1 we factored out, it'll come out in front of the limit using a limit law. And we're finally left with the limit as x goes to c of 1 over g of x g of c times this minus f of c times this. Okay, so we're almost there. So I just cut and paste this over from the previous page so we can work from what we saw there. Now I'm going to evaluate my limits. So here we know g of c is differentiable at c. So that means that g is continuous at c. So that means by the limit laws, this first term, that the limit as x goes to c of g of x is g of c. So my denominator becomes that in the limit, which shouldn't be a surprise. And then we've already talked about this. This limit here is exactly the definition of f prime of c. And the other limit, we worked hard to put it in the form of the limit definition of g prime of c. So there you go. Just rewriting. This is the formula we were looking for. And this proves the quotient rule. So let me just make one final note. Technically, what we wanted to show is that the limit definition of the derivative of f over g at c, that limit exists. So by going through all these steps and showing that these other limits here, that using the fact that this limit exists, and this limit exists, and this limit exists, that all tells us that the limit we started with exists. And it turns out the value is exactly this. So by using the fact that these limits here exist, we showed that the limit in question we began with exists. And then we got more information, indeed, that the formula for the value of the limit is the one here circled at the end. And that's the proof of the quotient rule. So with that, I'm done. See you next time.